If your steam system has pipelines longer than 50 meters, or if the steam must pass through pressure-reducing valves, regulating valves, or special control valves before entering factory equipment, installing a steam separator is a very reasonable solution to protect these valves. Installing a steam separator helps the valves operate more stably and reliably, while reducing minor damage caused by water hammer due to condensate carried in the steam. In the previous video, I compared the real operating behavior of different types of steam traps. In today's video, I will conduct a visual experiment on the operation of a steam separator to evaluate its actual performance together with you. Before moving to the experiment, I will briefly introduce the operating principle of the steam separator, as well as its manufacturing process. The main function of a steam separator is to remove water droplets from the steam or gas flow, increasing steam dryness, because water droplets carry much less useful energy than dry steam. In addition to moisture separation, the steam separator also has a notable secondary function, removing impurities carried in the steam. During actual operation, impurities such as welding slag, paint and sand generated during piping and equipment installation can be carried along with the steam. The steam separator is very effective at capturing these impurities when they are entrained in the steam flow. By contrast, conventional condensate collectors alone are almost unable to remove solid particles and impurities carried by the steam. DIVI's steam separator is designed based on a centrifugal vortex principle, using screw-type guide vanes. This is a relatively complex design, but it delivers very high water separation efficiency. And now, here is an overview of the manufacturing process of this steam separator. All welding joints are performed using TIG welding, which is shielded by inert gas to ensure the highest weld quality for pressure equipment. This is the machining process of the internal guide vanes. And here is the finished product after fabrication. Before delivery, the product is pressure tested at 1.5 times the design pressure and strictly complies with pressure equipment manufacturing standards. After that, the designs are further tested to verify real water separation performance before mass production. To test the steam separator in real conditions, a steam source is obviously required. Therefore, we operated a 1-ton boiler using pellet fuel. This is a 1-ton pellet-fired boiler designed and manufactured by DIVI for export markets. The steam from the boiler is passed through a heat exchanger to increase its moisture content, simulating steam quality after traveling through long pipelines in real systems. This process partly reflects the wet steam conditions commonly found in operating industrial steam systems. This wet steam does not pass through a steam trap, but is fed directly into the steam separator. The steam inlet is split into 2 branches, one passing through the steam separator and one bypassing it. Both outlet steam jets are directed in the same direction, allowing direct visual comparison of steam quality in both cases. The bottom pipe of the steam separator is the condensate discharge line. In this experiment, no steam trap is installed on the condensate line so that the behavior can be easily observed. Now we will supply steam to the system. You can clearly observe that the steam branch without the separator carries a large amount of water. Meanwhile, the steam passing through the separator carries almost no water, and the discharge steam is barely visible. In contrast, a large amount of water is discharged from the condensate outlet at the bottom of the separator. This clearly demonstrates that water has been effectively separated from the steam. From the amount of discharged water, we can see that a significant quantity of condensate is actually carried by the steam. If the installed steam trap has an insufficient discharge capacity compared to the actual condensate load, it will not be able to drain all the water. As a result, water continues to be carried with the steam, keeping the steam wet. To directly verify the steam quality of both flows, I place a barrier between them and use a dry sheet of paper to capture the steam. This allows a direct visual evaluation of steam dryness and quality. When the paper is placed in the steam flow, without the separator, it becomes wet almost immediately. In contrast, when the paper is placed in the steam flow that passes through the separator, it remains completely dry. This proves that water droplets have been effectively removed, resulting in much drier steam. Let's observe the paper test once again. This time I remove the valves at both steam outlets to eliminate their influence on the observation. The result shows that the paper on the non-separated steam branch still becomes wet very quickly. Meanwhile, the paper on the steam separator branch remains completely dry. At this point, the moisture separation effectiveness of the steam separator is clearly evident. The next question is, why do we need to separate moisture? And what is the real purpose of doing this? This topic will be analyzed in detail in part 2 of the video. Please stay tuned for the next part. Thank you very much for watching and see you in the next video.